Okay, this is a second video for the direct comparison and limit comparison test for infinite series for calculus. This one, we're just going to go through additional examples. So let's take them one at a time. For this one, let's try, I think it would be instructive maybe to do every one of these by both limit comparison and direct comparison, just to see which will work. Okay, so let's try both. Let's try direct comparison first. So let's assume we're going to do a direct compare to something simpler, and we usually get that by just dropping a constant. So that would be 1 over n cubed. That is a p-series. P is 3, so therefore that converges. Large values in the denominator converge. That converges. And then for direct comparison, we now have to compare. So I think we have to write this. 1 over n cubed is less than or equal to 1 over n cubed minus 1, because if you subtract something from a denominator, that makes the denominator smaller, which makes the fraction larger, so it stays above that. Let's see, we have a comparison for convergence there. This one, the simpler one, converged. Is that right? P series 1 converged. Is this right? This one? Yeah, so this one converged. So I think in this case, is this right? Yeah, if I subtract 1 from the denominator is getting smaller. So yeah, the fraction is getting larger. And that means that this other side over here just has to stay above that. So it could diverge, or it could converge, but it also could diverge. So actually, this is the wrong side for direct comparison to work. So that won't work at all. We definitely have to do limit comparison, but we'll again compare to that same series. So I won't redo that work, but to switch to limit comparison, if we're doing limit comparison, we'll take the limit as n approaches infinity of the two rules, a n, b n. So that would be the limit as n approaches infinity of 1 over n cubed minus 1 divided by 1 over n cubed, which is the same as the limit as n approaches infinity of n cubed over n cubed minus 1. You could use L'Hopital's rule 3 times, or you could just say, hey, same degree, this ends up being 1 over 1, which is 1. That's a finite positive number. That means these series are linked. So then we could say this then, since the limit as n approaches infinity of 1 over n cubed minus 1 and 1 over n cubed is 1, I'd like to point out that that's a finite positive number. Therefore, the series are linked, and since the series n equals 1 to infinity 1 over n cubed converges by the p-series test, therefore the series n equals 1 to infinity 1 over n cubed minus 1 also converges by the limit comparison test. Right, so in this case, the direct comparison test won't work at all, and you'd have to use limit comparison. Okay, let's take a look at another example. For each of these, of course, you could pause the video and give them a try, and then unpause and see if your answer matches mine. Okay, so for this one, same thing. We're going to go ahead and pick something to compare with. Just drop this plus 2. Let's compare. I'll do this in the middle here. We're compared to the sum equals 1 to infinity of 5 over 3 to the n, which is just bring the 5 outside, n equals 1 to infinity 1 over 3 to the n. And this one is actually geometric. If I continue this is 5. Actually, maybe I'll put that back inside there. This is a sum from n equals 1 to infinity 5. And then this 1, you could write that as 1 to the n, which makes this 1/3 to the n power, which makes this geometric. with r equals 1/3. Since the absolute value is less than 1, that means this converges. So we have a similar series that converges by the geometric series test. Okay, let's try direct comparison. If we try direct comparison, we have to determine the sides. So I would write this: 5/3 to the n is less than or equal to 5/2 plus 3 to the n, because if you add things to denominators, the fraction gets smaller. So wait, I just wrote that wrong. Let me go backwards. Adding to the denominator makes something smaller. Right, so this would be the correct direction. Now we just showed that the new series converges, and that's this series. And sure enough, if this term is always underneath that, these terms are underneath that, it's also going to converge. So this is the correct side for direct to work. All right, so then we can just say this: since 5/2 plus 3 to the n is less than 5/3 to the n, and the series n equals 1 to infinity of 5/3 to the n converges by geometric series test. Therefore, the series n equals 1 to infinity of 5/2 plus 3 to the n also converges by the direct comparison test. Okay, so direct comparison will work. Of course, I think we can also use the limit comparison test. Let's see what would happen if we had done that. We could choose the same comparison to do here, but then we could finish this. Now, you don't have to do it both ways. I'm doing this problem both ways to show that they'll both work. But you would pick one or the other, either direct or limit. You don't have to do both. So if we did limit comparison, we would be taking the limit as n approaches infinity of the two rules. So this would be, let's see, 5/2 plus 3 to the n divided by 5/3 to the n, which is the limit as n approaches infinity of, let's see, the 5's cancel out, and this will move on top. So it's 3 to the n over 2 plus 3 to the n. Right? And if you did L'Hopital's rule, maybe we should do it real quick. Limit as n approaches infinity of 3 to the n is infinity. Limit as n approaches infinity of 2 plus 3 to the n is also infinity. So we have an infinity over infinity, and you can use L'Hopital's rule to say that this derivative, same limit, as n approaches infinity of, let's see, it's a copy, but times the log of 3. That's the derivative of 0, so this is the same derivative down here, which means this limit is 1. Right? And then we can say, since the limit as n approaches infinity of 5/2 plus 3 to the n over 5/3 to the n is 1, which is finite and positive, and the limit of the series n equals 1 to infinity 5/3 to the n converges by geometric series test. Therefore, the series n equals 1 to infinity 5/2 plus 3 to the n also converges by the limit comparison test. Okay, so in this case, direct comparison will work, limit comparison will work. There's a little bit less writing with the direct comparison version. I apologize for the writing on this. I'm using a tablet, so it's a little bit shaky. All right, let's do another example. Same thing here. Let's try to compare to, see if I write a little bit bigger, compare to the series n equals 1 to infinity. I'm going to drop this plus 4 on the top. So 3 to the n over 2 to the n, which is 3 halves to the n. That is geometric with r is 3/2, so since the absolute value of r is greater than 1, this one diverges. Okay, let's try to do direct comparison and see if that works. Okay, so what happens if you add things to the numerator of a fraction? That will get larger, right? So that means we would have 3 to the n over 2 to the n is less than or equal to 4 plus 3 to the n over 2 to the n. And we just determined that the simpler one diverges, so that is on this side, right? And if these terms are above that, they are going to be pushed to diverge as well, so the direct comparison is the right side that you can use. You could go ahead and do this and say, since 3 to the n over 2 to the n is less than or equal to 4 plus 3 to the n over 2 to the n, and the series n equals 1 to infinity of 3 to the n over 2 to the n diverges by geometric series test. Therefore, the series n equals 1 to infinity of 4 plus 3 to the n over 2 to the n also diverges by the direct comparison test. So that's a good way to do that problem, direct comparison. Okay, let's switch. Let's say that you wanted to try limit comparison. Some students just say, you know what, since limit comparison doesn't depend on side, it works in more cases. So some people will just always go to the limit comparison test first. But whichever it works, if one test shows that it's diverging, the other test also has to show it's diverging. So if we decided to choose to do limit comparison, we would take the limit as n approaches infinity of the two rules. So 4 plus 3n over 2 to the n, and then 3 to the n, 2 to the n. That is the same as limit, let's see, these are going to cancel out. So you're going to end up with 4 plus 3 to the n over 3 to the n. All right. If you were to do L'Hopital's rule, the limit on the numerator would be infinity. The limit in the denominator would be infinity. And since you have it in an indeterminate form, you can use L'Hopital's rule. So now we would have the limit as n approaches infinity of the derivative here is 0, so that's going to be 3 to the n times the base, natural log of the base. Same exact derivative on the bottom, so that's 1, finite and positive, therefore the series are linked together. All right, so we can write that up. Since the limit as n approaches infinity of 4 plus 3 to the n over 2 to the n divided by 3 to the n over 2 to the n is 1, which is a finite positive number, and the series n equals 1 to infinity of 3 to the n over 2 to the n diverges by geometric series test. Therefore, the original series, n equals 1 to infinity of 4 plus 3 to the n over 2 to the n, also diverges by the limit comparison test. Okay, so here's another example where both the direct comparison and the limit test will work. But there's more writing and work involved in the limit comparison test. The downside to the direct comparison test is if you have a case like this first one where it doesn't work at all, then you have to go through the work with direct comparison and then again go through the work with limit comparison to make it work. So while the limit comparison will work in more cases, it does involve more writing. Okay, so we've got 2 more. Okay, number 8. Let's do a comparison here. What will we compare to for this? Again, I'm going to try to imagine just dropping this plus 4. So let's compare to the series n equals 1 to infinity of n over the square root of n to the 5th, which would be the same as, let's see, n over n to the 5 halves, which if I want to write this in p-series form, I could write that as 1 over, and then let's see, if I took 5 halves and subtracted 1, that would be n to the 3 halves, right? Although we wouldn't normally write that way, if we write it that way, we can say this is a p-series with p equals 3 halves, and that one is going to converge, okay, because that's greater than 1. All right, so now let's try a direct comparison test. And if we do a direct comparison test, we would have to somehow establish which one of these is above the other. Now this is where I can't really tell easily this. N over the square root of n squared plus 4. Well, no, I guess I can. That is going to actually be below that, right? That plus 4 is going to make that denominator smaller in all cases. So that means that will be less than this. We just determined that the new series converges, and that goes down. And so if these terms are staying under net, they are pushed down. So actually direct comparison will work. Now let's finish that then. We can just say since n over the square root of n fifth plus 4 is less than or equal to n over square root of n to the fifth, and the simpler series, n over the square root of n fifth, converges by p-series test. Therefore, the original series, n equals 1 to infinity of n over the square root of n to the fifth plus 4. This writing's getting pretty bad. N to the fifth plus 4 also converges by direct comparison test. Okay, so direct comparison works. Can we do limit? Usually, if direct works, limit will work. So for the limit comparison test, we could have alternatively chosen to do n over the square root of n to the fifth plus 5 over n over the square root of n to the fifth. Right, these n's will cancel, and say we're finding the limit as n approaches infinity of the square root of n to the fifth over the square root of n to the fifth plus 4. Okay, so at this stage, maybe I would just look at that and say, wow, this is a hard limit to compute. With radicals, L'Hopital's rule is not going to work really well. So I think at this point I would abandon that and switch over to direct. There's too much work involved to try to do the limit. But thankfully, direct was on the right side. Okay, let's take a look at this. Now this one says use limit comparison. Why did we say that? Did we just do this one with direct comparison? Now this is actually the same one that we did over here. I think in this example I was trying to show that we could use direct or limit. Okay, so we'll skip that since we've already done that. Okay. All right, I think that should be it for the examples. If you need more, of course, there's also posted solutions for the homework.